All right, hello and welcome to the programming lecture for the week. We are going to talk about more animation today, and we're going to have some fun with our bouncing ball. So last time we did quite a few things. We made this fancy program called Bounce. That was one of the things. And what it does is, if I run it and remind you, it takes this ball, and I guess it starts in a random position, and it's going to bounce it up and down. And you might be wondering, why in the world is this creating any kind of animation? Like, this is what's redrawing things. It's this forever loop, essentially, while true, forever do all of this, right? And I talked about frames, like, gotta draw a first frame, then a second frame, then a third frame, and then it looks like people are changing. Like, here's like a person moving, right? We didn't really work with these, did we? What we were, I guess, maybe something that you could be thinking is, well, if the program is just drawing a bunch of frames repeatedly forever and ever and ever, like, how does it have any time to show them to us? Like, it shouldn't ever show me anything, right? And the answer is no. It is doing weird things, yeah? So it's not showing frames so fast that you don't see anything. It's not always redrawing the screen. It's actually taking some time. Okay, and that is the key, okay? Most computers take a while to draw to the screen, and so all this stuff in here takes a certain amount of time to perform this update. Like, okay, I have to run this line. This takes, like, I don't know, a nanosecond or something. It takes time, though. This turtle.goto is probably the most complicated thing, and it actually moves the turtle, and that might take, I don't know, a few milliseconds. Maybe something like that. And that is where we get our animation from, because there's a little bit of time in between each drawing. And so we said, okay, ball, start here, and then in our while loop, we changed its position ever so slightly. It took some time to draw this. It took some time to draw this. And so there really was a difference between the frames. It's really putting them there and showing them to us, okay? We're really getting individual frames out of this, even though we're not thinking that way, okay? If you wanted to really, really control how often your frames are redrawing, because maybe on my computer it's slower than yours, and so this program might look a whole lot faster than yours. Maybe the ball bounces faster for you because your computer can draw the turtle a bit faster, yeah? That's quite possible. So you can change the real frame rate by telling your program to wait, okay? Time.sleep. It tells Python to wait, okay? So you can say time.sleep and like 0.01 or something, and this will draw 100 frames a second because it's going to sleep every 0.01 seconds, yeah? Hopefully that makes sense. So that's telling Python, hey, stop running the program. Make it stop for 0.1 seconds. Make it stop for 1.5 seconds. Okay, so let me just show you that. Here is the time library. You can import that, and it's got plenty of things, but the one we care about is called sleep. There it is. So you give it a number of seconds, and it stops the program for that long. It has a very fancy way that it says it stops the program. Suspend execution of the calling thread. That just means it stops the program, okay? So I can say import time, and I can say time.sleep, I don't know, 3. Are you ready? Are you ready? Look how it does nothing. It's just sitting there. It sat there for 3 seconds. See that? I can make it faster. Time.sleep for 1.5 seconds. See? It waits for 1.5 seconds. And so that's what you can be using, potentially, if you wanted to like slow down the turtle a little bit. Okay? We can totally do it that way. I don't want to change this because this is the code from last time, but I hope you get the idea. So that's really why we're getting animation out of this. It takes some time to draw the turtle, and that is going to actually produce a new frame for us while it's waiting to draw the next turtle. Okay? Please yell at me if that doesn't make any sense at all. That is the idea, though. Now, I want to make the ball bounce in a cooler way, all right? I hinted at this last time. I want it to, like, start here and then bounce and, like, speed up because gravity. Like, we go fast. Bounce, bounce. Like it's gonna go up and then down really fast, right? And then it bounces really fast. Hopefully that weird drawing made some sense to you. I'm going to show you in a second, though, once we get it completely running, what's going to happen. All right. So we want that ball to move with gravity. We want it to be slow up here, but once the ball gets down here, we want it to go a bit faster. And then it's the fastest when it hits the ground. And it's the same when it's bouncing back up. It should be very fast down here, but it slows off once it gets to the peak of its bounce. Yeah, that's what real life bouncing balls should look like. Yeah, and the way we can model that is with good old kinematics. So if you've taken a physics class, this is going to be old news to you, but it's a really exciting application of physics in our computer programs. So yeah, right now our ball, it's moving with constant velocity. Okay, it's moving at the same exact speed. Does that make sense? Because I'm changing it. I'm changing the offset. I'm using the offset. The offset never changes, so it's moving by a few pixels a second. Okay, that's the idea. And so I'm going to copy all of this before I forget, and I'll make a new file, paste it, and we'll make a new folder for ourselves. This is going to be lecture 25, I assume. And so I'll call this bounce gravity.py, and this is going to be lovely. Okay, so most of this gets to stay the same though. Now I can add more comments though. So the turtle's y-coordinate, it's changing by a certain offset, and that is like pixels per second. Okay, it's like change by how many what's our offset? Where did it go? Oh, -5. Change by 5, because it might be negated down here when it bounces off a wall. Change by 5 pixels up or down. Yeah, you can think of it that way. 5 units. And that is our speed. Our speed is constant. We always, in between frames, change our speed by 5, either up or down. Okay, so it's moving by 5. And I can say move by 2.5 instead, and it will move half as fast, because it's moving only 2.5 units per second. Yeah, that is the idea. And so let's keep it like that. That's fine. It can start out like that, but the idea of kinematics is that, and the idea of real life is that things bounce not with constant velocity. Okay, they speed up as they get closer to the ground. Right, ball should speed up on its way down and slow down on its way up. Okay, so the age-old question is, how fast does a ball in real life change its speed? And now we need to bring a new element into the equation. What does it mean to change your speed? That means you have a certain amount of acceleration. Acceleration, remember, is how fast your speed changes. Acceleration is defined to be the change in your velocity. Isn't that beautiful? So in real life, we are accelerated by gravity. That's what's changing our velocity. If we just jump from like the top of a diving board, we initially have no velocity. Like here's us on a diving board. We initially 0 velocity, but as we start going down, gravity's pulling us at a rate of 9.8 meters per second squared. So all this means is you speed up by 9.8 meters per second every second. Okay? So that's the beauty of it. That's what the ball should be doing. It should be speeding up by 9.8 meters per second every second. That's where the squared happens. Okay? So the way that we can have a bouncing ball affected by real gravity is to have an acceleration variable. We can have our own acceleration variable. It can be 9.8, but we might need to change it so that it doesn't like look too fast to us. This can change. It's just going to be a certain number of units. And then we'll also have velocity. Okay, we already have velocity, but we want to start it at 0 and have it be affected by acceleration every frame. Okay, that's the hope. So now we need the addition of this variable. We need acceleration, and that needs to change our velocity. Our velocity cannot always stay the same anymore, because that gives us this smooth animation. We don't want it to move exactly the same speed every time. We want it to speed up as it goes down, and so that means our velocity has to change. Our offset has to change. So I guess the first thing that I want to do is change offset to velocity, because that's really what it's representing. Yeah. So let me do that. Let's see the best way to do this. There we go. That'll work. So I'm going to change this from turtle offset to turtle velocity. And I want it to start at 0, in fact. Whee. So velocity, how fast we're moving. And it starts at 0 because we're just jumping off of the diving board. We're not pushing down. We're just letting gravity start pulling us, start changing our speed. Okay? And then we'll do turtle acceleration. And I have no clue how fast to make this, because it's going to be, it's not per second for us, it's per frame, right? So for velocity, the units are like how many pixels per frame, and acceleration would be pixels per frame squared. Okay, so I'm not sure how fast to make this. Let's start at like 2 or something, and then we can play with it later. So it's like pixels per frame squared. Yeah, so we'll see if that works. And now I want to, instead of offset again, I'm going to say velocity everywhere. Whee, velocity. Velocity changes if we hit a wall. That's fine. And actually, I want us to start moving downwards first, so I'm going to make it a -2 acceleration. Okay. And actually, I think the direction should be... No, that should work. I think that should work for now. We'll try it. Okay, well, let's see if there's anywhere that I said, what was it? Anywhere that I still said offset. And I think we're good. So, yeah. So acceleration is some constant, and that's the constant now, and velocity is being changed by the acceleration. Okay? So, here's the idea. Forever, we want to draw our frame, draw our ball, and move it a little bit by its current velocity, okay? But we also want to change the velocity every frame, okay? Every time a frame happens, we need to let the acceleration affect our velocity. So in addition to this, we have to say use the acceleration to change the velocity. Okay, so we'll say turtle velocity. That should be affected by acceleration. Plus equals turtle acceleration. Okay, that is the idea. So every frame, every second, we want to speed up or slow down. We want to speed up in the y direction, in the negative y direction. Okay, so that's what we want. So we're going to use the acceleration to change our velocity. If our velocity started out being 0, it's now going to be -2 and start pulling us down after one frame. It's going to be -4 after the next frame, pull us down even faster. This might actually be too large. Maybe let's make it 1. That might still be too large, but we'll find out. So really, this line is doing a lot of hard work for us. Okay, and then we want to take a look down here and make sure that everything else is still okay. So we want to check if we hit a wall still, of course, and bounce off it. But really, we're only ever going to want to hit the bottom wall. Okay, that is the hope. We should never have to hit the top wall anymore, because we shouldn't. We should only bounce back up to where we started. Okay, that is the hope. So we shouldn't ever have to hit the top wall, but we can keep this code in there, I think. And And then when we hit the bottom wall, though, that is when something needs to happen. So the second we hit the bottom wall still, we're moving at some speed, some very fast speed, right? And we want to bounce off at that same speed in the opposite direction. So I think we can actually keep our velocity the same, yeah? And then it's the acceleration once more, of course, that's going to bring the ball back down as it tries to go higher and higher. The acceleration is always in the negative direction. So there's always that acceleration way over here. I'll call it A. It's always going to be trying to pull us down, okay? And so I think we have a good shot at it doing something almost correct. Let's try running it. Really, it's just this one line. I added this acceleration, and I affected the velocity by the acceleration. And velocity was already a variable that we used, I just gave it a new name. Ooh, isn't that fun? So yeah, it's way too fast. Let's fix that. Let's make it, I don't know, negative 0.25 acceleration. See how that works. Ooh, that's getting better. 0.1. That's almost better. That's almost perfect, honestly. I think it's still hitting the top, though. Let's see what we can do about that. Negative 0.05. Whee! Yeah, I think it's going right up to the top is the idea. So maybe if we don't start at the top, it will go to the middle. So let's try starting the ball somewhere not at the very edge. Let's see if that does anything cool. Okay. Let's see here. I liked 0.01. Let's see here. Where do we start the ball? Let's start the ball like 25 down or something from wherever we were. Oh, look at that. Look at that, guys. Look at that. Oh, I think it's gaining speed, actually. That might be a little bug that we'll have to look into. Yeah, because eventually it's hitting the top of the wall again. Yeah, let's start it down at 50 then and see what we can do about that. Because that's quite nice. That is working quite well. Yeah. I think it's going to ever so slightly start gaining speed because I think what happens is we let it go a little bit farther down below here. And that's... See, we hit the bottom when it goes past the bottom, okay? It secretly goes past, but we don't draw it there. And that, I think, is what's biting us here. That's what's allowing it to speed up a little bit. So I think if I do this, if I get rid of this line, that will allow it to slow down properly, or speed up properly. Let's see if it's going to go back up to the top again. Yeah, just a bit, isn't it? So that's not the answer. But that's very close to being perfect. So I'm going to stare at this code for a little while and see if I can figure out what's causing it to do that. Because it's almost there. And I think I remember what I did last time. It is because it's going past the bottom a little bit, and so it allows its velocity to increase past the borders of this box. So I think we do want to keep this, but we also want to figure out what the velocity is, what it should have been when it hit the real bottom. See how it's kind of going past it there? We don't like that. So let's print out the velocity and also the turtle y. So let's do the turtle y, and then the velocity. And see if we can figure out what it should be once it hits 0, and that's what we can set it back to. It's kind of a cheating, but I think that's what it should be. Let's see here. Velocity when it's at negative 180. Initially, it was about 8. See that, negative 8? So I think if we set it to be negative 8, that will fix this. Because then it will stop increasing like that. I think as long as we reset it, it should be okay. So I think if we set it to -8, that should make it happy. And then we're about to negate it to make it go back up. So let's just make it +8. Okay, let's try that. That means this is no longer necessary. We're handling that in the line above. So as long as it bounces and we set it back to 8, I'm pretty sure, based on where we started it, it's always going to bounce up to the same spot. Let's see if I'm going to eat my words. And now we have, my friends, we have a bouncing ball that bounces ever so perfectly. Speeds up as it goes down. I'm not sure how the video looks for you, because maybe like my recording software doesn't show this as cool as it looks, but do run this program. Play around with the acceleration to make it go faster. The issue with that is you'll have to change this hard-coded velocity value, but that is beautiful, huh? And I just played around a little bit more. I doubled essentially the acceleration, and then the correct velocity for that was 16, and I think it looks quite nice and bouncy now. Okay? So isn't that fun? This is a nice little bouncing ball for us. And one thing that we can do is make it even more like real life, in that the ball, it slows down a little bit, right? Every time it hits the ground, it's not a perfectly elastic ball. It's not a perfectly elastic collision for physics terms. What we can do is we can have the ball lose some of that fancy perfect velocity every time it hits the bottom. So here's what we can do. We can say total velocity equals 16 minus something, right? Or we can say max 0. 16 minus, I don't know, what should we do it by? 0.5 times some variable I. And every time we hit the bottom, we increment this thing called I. And we start I at, I don't know, 0. This I will keep track of how many times we've hit the bottom. And it will keep on taking away our bounce velocity. Like, slowly reduce, with more and more drops, because that makes this number bigger. Slowly reduce our bounce velocity until we're standing still. Okay, it'll become eventually 0. Okay, that is the hope. This will surpass 0. So that's why I did the max. Okay, that is the hope. And as long as we increment I, that might make it beautiful. Okay, let's try this. Moment of truth. So every time it drops, I is incrementing, and you see how it's losing steam? This is what a ball really does. Isn't that awesome? Yes, yes. Was that not the most satisfying animation you have ever written? Okay, that is everything. Let me add that for posterity. We can add a variable to slowly reduce our bounce velocity. And unfortunately, I just moved everything. I think it was like that. I can't remember, sorry. Now everything looks a bit odd. Maybe I should just get rid of those little lines there. Yeah. So, I think we've come a long way. And it didn't take that many lines, remember. We just added acceleration to change our velocity every time. We just had to keep track of how it's changing our velocity every time. And then we also figured out, like, okay, every time we bounce, maybe we should take a little bit off our bounce. Yeah, that is the hope. And that will cause, eventually, our ball to lose steam and to slowly bounce down to the bottom. Okay, I think that's everything. Let's make sure this is still recording, yes. And here's our beautiful bouncing ball, and please do study this program. It's a fun one. It's not too different from what we had, but it produces a very satisfying effect, I think. Okay, so that is, I think, everything. Do yell at me about any of these extra lines that I added. If they don't make any sense, please yell at me. This is important. I want you to understand this stuff. Okay, so that is essentially the job for today. That's what I wanted to talk about, how to make the ball actually look proper. Next, I want to talk about how to make a square bounce on the screen. So we have had a ball bouncing, we've had a ball bouncing now in one dimension. Really, it's only been one dimension, even though we thought about it as two, because it's just moving down and up, straight down, straight up. What if we could have our ball bounce around? Yeah? Like that DVD logo for The Office. So, in case you have forgotten about this iconic scene, let us go to this. So, it's that. We want to make that little DVD logo thing that bounces off every corner of our screen, okay? And so we can make our turtle a square instead of a circle, and hopefully eventually it'll hit that tiny little corner there and life will be good. Okay, that's the hope. So that is what I want to do. We're not going to do it today. We're going to figure out how we should do it. We're going to come up with a game plan for how to program this ball bouncing in multiple directions, okay? And that'll be the topic for next lecture, or next programming lecture, that is. Are you ready? So, again, when we do this, we want to draw the boundaries of the screen, as usual, like always, okay? So, we're always going to draw that little rectangle, just like we've been doing, and then, instead of a circle, let's make a square in a random location within those boundaries. So it can start here if we wanted, or it could start somewhere in the middle, and that's probably the most common way it's going to happen. Okay, now this is the key. We want to give the square a random direction to follow, just like a random direction in Scratch. Okay, that's totally possible. This is how we did our Pong example in Scratch, right? That's the idea. So, okay, we give this a random direction. Maybe that's it. And then we want to move this box in that direction until we hit a wall. Yeah? The second we hit a wall, like the box is right here, because it moved up, we then need to bounce off that wall. Okay? So we keep moving in our current direction if there's nothing in the way. But the second there is something in the way, we have to bounce off of that wall and change our direction accordingly. You see that? It's going to move to here. And so then the ball, or the box, will eventually move to this spot. Will eventually move to this spot until it hits this wall. You see that? And then it'll more or less bounce off in the same direction, like that. Okay? That is the hope. So, okay, that is the goal. We now, though, have a second axis, and that makes all the difference, okay? We just have to bounce when we hit a wall, but what does that even mean, to bounce? Like, what does it mean to store a direction? What does that what are we talking about at all right now? Okay, so that is something we need to talk about. A lower level game plan, okay? So, I guess the first thing that we need to remember to do is make the turtle a square this time instead of a circle, and then that turtle will have coordinates, okay? I think it's the middle part of the turtle. That's where the coordinates lie. And now we need to figure out how we're going to represent the direction. Like, we want the turtle to travel in this direction. What does that mean, okay? And now I want you to come back to how we were doing it for the bouncing ball. The way that we told the turtle to move down initially was to give it a negative velocity, right? And initially, if you remember the example from not this class, but last class, we gave it essentially a velocity of negative, what was it, 5? And that started dragging it down because we kept on using this to offset its current y position. So it's like, okay, move here, please. Move here, please. -5, -5, -5. And eventually it'll hit the bottom. And then we'll make it +5, +5, +5, so that it goes back up. Yeah? If we want to store a direction for our little square that's moving both in the x direction and the y direction, it's going sideways, we can do a similar thing still. We can store a velocity. That's totally fine. We can store that direction. But we can't just use one offset anymore. We have to use two offsets. Okay, that's the only big difference. That's really it. Okay, so here is how you represent a direction for a two-dimensional bouncing square version of a turtle. Okay, this is what you do. You save, if you want the turtle to go this way, if the direction is supposed to be represented by this arrow, it means in one frame we want the turtle to end right here. Yeah? What you store is this distance. That's the x distance, the change in x. Then you store this distance, the change in y. And if you change the turtle's x by that much and the turtle's y by that much, you better believe that box is going to go right there next time. Okay? That's what you do. So that's what we need to save now. It's like an x velocity, a y velocity. Okay? So it's just an offset. Okay? So each frame, we move the turtle's x-coordinate and y-coordinate by that amount, by that change that we want. Okay? And that'll cause the square to move to the new spot. Okay? So every direction, just remember that, in two-dimensional space this time, has an associated xy offset / velocity. Okay, so maybe we want the turtle to move from here to, I don't know, boop, 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 to here every frame, and this is go increase your x by 3, increase your y by 2. So our change in x that we want to give to our turtle should be 3, our change in y should be 2, and we can package this up in a nice little offset. Okay? So if the turtle starts at, I don't know, 1, 1, we want him at the next frame to move that way. Well, the new turtle's location should become 4, 3, right? And the way we get that is by taking the 1, 1, we take the 1, the initial x-coordinate, add the delta x. We take the 1 initial y-coordinate, add the delta y. Yeah? That's the secret. And this will turn the turtle's coordinate into 4, 3. And then it'll know to go right here next time. Okay? Hopefully that's making some sense. It's just, instead of one variable to keep track of where the turtle's moving, now we have 2, right? We have to worry about how it's changing in the x direction and how it's changing in the y direction. Okay, that's how we can make that easier on ourselves. And so that's how we'll program it. Okay, we're going to have these offsets, an x offset and a y offset that will be like the velocity on a certain axis. Okay, that is the key here. Okay, so the very last thing we need to figure out how to do is how to bounce off the walls. All right, so remember the coordinates of everything. So the way that we're going to do this, we'll just use the initial screen from last time. This was of height 400, this was of width 400, and this is negative 200, 200, right? This was our bounding box for everything. That's exactly what we have here. That's where we draw our rectangle, see? So that's the space that we have to move around in still. We'll just have a different program in that space. We have our box, we have its direction, which has a y offset and an x offset, and we need to figure out when we hit the wall, okay? So it looks like what I'm writing here is about when it's hitting the left wall, so let me change this up a little bit. So let's pretend that the direction was kind of like this, yeah? So it has still a certain x offset and a certain y offset. The x offset's negative now, y offset is positive. And so the turtle is eventually going to find himself right here. And we need to discover the fact that the box / turtle has hit this left wall, and we need to bounce him off like that. Okay, so how do we do it? Well, let's figure out how we're doing it right now for the top and bottom wall, because it's very, very similar. See, this is how we know that we hit the top wall. Okay, when we tried to go past the top edge. Yeah? That's what it means to hit the top wall. We tried to go past the top edge. We hit the bottom wall when we try to go past the bottom edge. Okay? So we hit the left wall. That means when we try to go to the left, we try to go out here, but we couldn't make it. Okay? That means that our x coordinate essentially was less than or equal to negative 200. And we have to account for the length of this box, but we'll deal with that later. Okay, let's just pretend it's an even negative 200. So the second we try and move our box out here, we should stop and bounce. Okay, and similarly, if we're going to try and hit the right wall, that means that our boxes slash turtles x coordinate was greater than or equal to 200. Okay, because here is 0, 0, and here is like 200, 0. That's the idea. So that's what we want to check for. Yeah, that is the hope. And yeah, we've already done the top and bottom walls, and that involves checking the y coordinate instead of the x coordinate. Okay, it's still all the same as we did right here. Check the y coordinate instead of the x coordinate. Okay, now we need to figure out how to bounce. Okay, because if we hit the left wall, we need to bounce. If we hit the right wall, we need to bounce. Top and bottom, we need to bounce. What needs to happen here is the big question. So let's think about this. Let us take a step back. So we have a way to figure out, like, hey, we hit the left wall. Now, if our direction was this, the direction needs to become this. You see that? I'm going to try and make this as accurate as possible. Let me make bigger arrows, in fact. Our direction used to be that. Now it needs to become this, right? That's the correct bounce direction. Let's talk about what it went from and what it went to, yeah? So, notice that here is our delta y, right? Is that changing? If we want our box to bounce off this wall, is it still going to increase in the y direction? And the answer is yes. So we don't actually have to touch the existing original delta y, our y offset, because we still want to go up after we bounce off the left wall. What needs to change, though, is our delta x. It used to be taking us to the left. Now, you see what it needs to do? It needs to be taking us to the right. So whatever it is, it's just the negation of the old one, okay? That's what you do. You negate one of your offsets, okay? If you hit a sidewall, you negate the x, okay? So sidewall, negate x offset. If you hit a top slash bottom wall, you negate your y offset. And let me show you this working with a small little drawing up here then. Let's pretend, here's our wall. Yeah, let's do it like this. Here's our wall, here's our box, and let's pretend that this is, I don't know, this is exactly negative 200 and, I don't know, 15 or something. And our direction that brought us into this wall was, let's just pretend it's delta x equals negative, I don't know, 2, and then delta y equals positive 3. So that's what brought us from like here to the wall. And then we want to bounce off in this direction, and that means we need to negate our x offset. So it needs to become 2. Delta x needs to become 2 now, and the delta y can stay the same. We still want to go up. We still want to bounce up. Yeah? And so that means our new location should become, after this, we move away from the wall because we changed our delta x, so it's negative 200 plus 2, so negative 198, and then we still add 3, so 15 plus 3 is 18. So that brings us up here. You see that? that's what it means to bounce off the wall, and that gives us the proper direction as well. So yeah, if you want to see top/bottom, even though we've done it already, let me just draw that quickly. And that will bring us home. Okay, so here's like the top wall, and here's the box. And let's pretend that, I don't know, our direction was whatever we ended up with here. It was 2, 3. So we came at it 1, 2, 1, 2, 3. All right. So here we are. So delta x equals 2, delta y equals 3. We're bouncing in this direction. We want to bounce off in this direction. You see that? And so that means keep going in the same x offset. Keep going to the right by 2. Delta x stays 2, but now go down. Delta y is whatever it was, not up though, not in the positive y direction, in the negative y direction, equals -3. Okay, do you see that? And so that gives us a new direction. It's called a vector, right? If you've taken physics, that is going to send us in the right way. Okay, so it's as if like this was our first direction. It was a right triangle. We had 2, 3. And then our new direction should look like this. It's still a right triangle with the same side lengths. It's just a bit weirder, right? It's still 2, 3. It just looks different in that we want to move down by 3, right? So we want to go from here to here. So that means go down by 3 and still right by 2, yeah? So that is hopefully making some sense. It's essentially that plus that gives us that, and that plus that gives us that, yeah? That is the idea. That's how we want to move around in 2 dimensions. Okay, so that's our game plan, and this is what we'll implement next time, and if it's still very confusing, don't worry. When I implement it next time, it should make a lot more sense. Okay, so the very last thing that I want to do is talk about your new extra credit, because I'm pretty sure this week your old extra credit, the one for Scratch, will have been due. So let me go here, and here is the new extra credit for Python review. Okay, so again, you can get up to 5% extra credit, and you do exactly the same stuff. Okay, let's see if I have accidentally, yeah, I remember like last time I did the same thing where I said 1.25 and 2.5 instead of 2.5 and 5. That is incorrect. So it really is 2.5 and 5 down here, and that is all. So here's what I would like. Again, if you want to do this extra credit, it's worth up to 5% extra credit. Option 1 is make a review video, and this is for reviewing Python, okay? You can just post a video just like last time, record yourself. If you want 2.5% extra credit, make a 15-minute video with a bunch of examples / explanations of things, and your peers will love you for it, and so will maybe my future students. And then 5% is 30 minutes. And option 2, you only have to do one of these. If you would prefer not to record yourself and write something up instead, you can, again, pretend you're writing a video, like make a little script maybe, have a bunch of examples of Python things, and like overview them, give examples, give solutions, explain everything, of course. And so if you want the extra credit there, you will have to have a write-up that looks like this. So at least 375 words for the 2.5% extra credit one, and then for the 5% extra credit one, make at least 750 words of a write-up. And this can all include code, in fact, okay? So you can just let Word or Google Docs just count your words even if you paste code into the document, because you'll probably be including lots of code, right? It's about Python, so all your code counts toward the word limit. So just let the word counter do its thing, like if you say if x is greater than 5, that's like 4 words, right? That should help. Okay, so that is your extra credit, and I think that brings us to the end of these slides. So hopefully you enjoyed the fancy bouncing, and do study that code. Please yell at me if you have any questions at all, and I will see you next week.